Okay, so for problem number 2, we notice that that formula, ignoring the negative 1 raised to a power, if we just take that limit as n goes to infinity, we do not arrive at 0. And we can feel very disappointed because we're not going to meet the criteria for the alternating series test. That's going to happen a lot. But look, there is one very, very, very valuable leftover test, and I mentioned it in lesson 12.2. It's a test that we're going to keep using all throughout this unit, and that's many weeks from now too, but it's the nth term test for divergence. The nth term test for divergence. Here's what I'd like to bring up. Just a moment ago I said ignore that negative 1 to the n. If I would have just gone back to this problem on section 12.2, and you wouldn't even have batted your eyes thinking, hey, that's an alternating series. You would have said, well, hey, maybe I could do the nth term test for divergence. Think about it. And I wrote this n a little too high, my apologies. This 3n all over 4n minus 1, of course, that's going to 3/4. But the negative 1 to the n, won't that continue to bounce between positive 1 and negative 1 as your power gets very large? Depending on whether your power is even or odd. Now, here's the issue. We don't know what infinity is in terms of being even or odd. In fact, infinity is simply a concept. So guess what we can say here? What is this limit? Guess where it's going? It doesn't exist. Yeah, it's bouncing between a positive 3/4 and a negative 3/4, with that negative 1 to a power. But more to the point, guys, that nth term limit isn't 0. And because that's not 0, now I can say by the nth term test for divergence, this series that we started with diverges. The nth term test for divergence will come to our rescue a lot. Please hear this. Every time you see that limit, ignoring the negative 1 to a power, every time you see that limit's not going to 0, your series will diverge. But you're going to have to come back and do this little bit of an extra step right here and say, look, what I'm seeing actually is throw that negative 1 to a power in, and that limit won't exist. It's bouncing around too much. More to the point, that limit doesn't go to 0. And anytime an nth term doesn't go to 0, that series diverges. Okay? So that's the official way to show divergence on section 12.5. Well, there's still more to the lesson that we're going to pick up. And this, wow, the alternating series estimation theorem is really something that gets used a lot. It shows up a lot on the AP exam, quite frequently, quite a bit. So we need to know it very well. What this is saying is, let's just say you've got an alternating series and it will converge. Let's just say that you are told that it converges, okay? Then you get this very obscure, weird-looking thing right here. You'd say R sub n. This R sub n in absolute value is really talking about error in absolute value. Today we get focused in on error. And that can look so strange to kids. They can look at that, they'll say, I beg your pardon, how could that be error? Well, if you have S is going to be the true sum. It's what that series would really converge to. By the way, unfortunately, we won't know what it truly converges to. There are really just two series that we've worked with so far where we know that. telescoping and geometric. Most of the time we don't get that. But there is a true sum. S sub n is the nth partial sum. So I guess what I'm trying to show you over here is, let's just say we went back to example 1 and someone said, hey, add up the first 5 terms. Add up those first 5 terms. By the way, the next term here would be plus 1/5, right? So you get your first, second, third, fourth, fifth. And someone said, hey, add up those first 5 terms. S sub 5 is what you'd be finding. Would that equal the true sum if we went on forever? And the answer is definitely no way, right? You'd say you're supposed to add up forever and you're only adding up the first 5 terms. You're not going to get the real answer, the real sum. So what are we seeing? We're seeing there'd be error. There'd be error. There is a real sum. You add up the first 5 terms, you're not going to be exactly at that true value, the true sum. You subtract and put it in absolute value, that's how much you're off. That's your error. Now, this is absolutely amazing. The theorem goes on to say is the error is less than or equal to the n plus 1 term. Wow. So that means our error would be less than or equal to, well, if I add up the first 5 terms, my error has to be less than which term? The 6th. The 6th term forms an error bound. So you'd say, hey, I just added up my first 5 terms, just like I did up there. You'd say, I wonder how much we're off. Do you know how much you're off? The next term would be a 1/6. Ignore the negative. Your maximum error would be 1/6. Wow. That's really something. You could say, what if someone said, you know what? That's not enough. I'm going to add up the first 100 terms. What would be your error bound? The 101st term. Do you see that? You'd say, I'm going to add up my first 100 terms. Wow, you're getting some number. Somebody'd say, I wonder how close I am to the real sum. Well, your error is less than or equal to the 101st term. Okay, so that's really what's going on here. All of a sudden we're finding, and the proof of that, I'm going to let you guys think about that. We'll talk some more about this down the road. Sometimes kids are, beginning to say, why is that? And we'll talk about that a little bit in the next couple days. But for right now, take it on good faith. First, we also need to talk about how to bound error. If E is that error, then the approximation will be considered accurate to k decimal places if the error is less than 0.5 times 10 to the negative k. Now that looks so weird. Let me tell you the truth, though. This is the better way to understand it. Look, you want 1 decimal place accuracy? Your error better be less than 0.05. Here's what I want you to notice. Here's that first decimal. Here's that 1 decimal place accuracy. We're always going to put a 5 next to it. But the error has to be less than that. Sometimes kids will say, what do you mean? Well, look, if it was equal to 0.05, wouldn't that 5 round up and change that 0 into a 1? See what I'm talking about? If I equaled that, that would allow us to round up and affect the first decimal point. As soon as you're smaller than that, you no longer would round up to affect that decimal place. That's what's going on. You could say, what about 2 decimal place accuracy? Well, 2 decimal place accuracy means go out to 2 decimal places with a 0 and then have a 5 here. If you are smaller, if your error is smaller than that, look, if it was equal to that 5 could round up and go to the second decimal place and turn it into 0.001 if we round it, right? If we're smaller than that, we can't round up and affect the second decimal place. So that's really what's happening. That's your error bound. If you could say my error is smaller than 0.005, that means that you're accurate to 2 decimal places. Okay? So we've got one last problem. And first of all, just want to make a real quick comment about 3 decimal places. 3 decimal places, you could say 0.000. That's 3 decimal places. I want my error, like we were just talking about, to be less than 0.0005. That's probably a better way to think about it. Go out to however many decimal places you want, what they're telling you to find. Go 0.000, stop, and then put on a 5. If you're smaller than that, you won't be able to round up and affect that decimal place. Okay, so that's really what's going on here. And they're saying, hey, would you find the sum that we have here correct to 3 decimal places? Wow. First of all, sometimes kids get very upset about this. N equals 0. They can say that's got to be a typo. Actually, no. You're going to start seeing sigmas where instead of starting at n equals 1, you will start at n equals 0. There are good reasons why we're going to do this. I hope it's going to make more sense down the road. But take it on good faith. It's okay right now. One other comment, though. Sometimes kids will say, it's not okay. Your 0th term wouldn't exist. Right? 0 factorial. Well, actually, what is 0 factorial? It's a 1. Look, just want to help you out here. You can take it by a definition that 0 factorial really is 1. We'll talk more about why that's true later. Don't want to have the video get into the taken away with that subtopic. But take it on good faith. It's okay to start plugging in n equals 0, and we're going to go out. And sometimes kids will say, well, how do I do this? How do I work up to being able to find a sum accurate to 3 decimal places? The answer, what you got to do, guys, is find a term so that it's less than or equal to 0.005. So that's our goal right now. Find a term, a b sub n if you would, or a b sub n plus 1 if you would, that's going to be less than 0.0005. So right now, guys, it's going to turn into kind of like guessing and checking. B sub n just itself is 1 over n factorial. And if I did 1 over n factorial, the big question is, what's the first term that I could plug in so that I will be smaller than 0.0005? So I'm going to go 1 divided by, and then type in some factorial. Let me take a suggestion. What should we maybe try? What's a good starting place? Good guess. Your guess might be as good as anybody else's, right? What's that? 9. Okay, if we did 9 factorial, that's going to be 2.755 times 10 to the negative 6. Well, my goodness, how would you write that? 5 zeros, 1, 2, 3, 4, 5, and then the 275. So that's definitely smaller. We want to find the first time, though, that is smaller, that our term is less. So maybe a 6? Okay, that might be a good thing. Second enter, maybe change the 9 to a 6 and see where we're going. Is that doing the trick? Not quite. 7 maybe? Let's try a 7. We can say, come over here, and again, with the 7, we can say, hey, would that do the trick? 1.984 times 10 to the negative 4